of ZTD connector solution. I think Mr. Dashtower explained the situation and the plans of Mongolia power grid. And now ZTD comes with solutions for the connector. We will try to give the best. I will illustrate from 5 aspects. First, I will briefly introduce ZTD connector factory. Actually, ZTD connector factory is acquired by a state-owned connector factory established in 1939. And till now, ZTD have the China production base and the Indonesia production base. And the annual production capacity is 220,000 tons. And the overhead line operation is more than 1,800,000 tons. So we will wait for a while to fix this slide issue. Okay. It comes with the ZTD connector factory brief introduction. And the ZTD, we design and manufacture different types of connectors, including the conventional connectors, low-loss connectors, and the operating connectors, as well as some other functional connectors adapted to different environments. And ZTD connector is widely used globally on different continents. And as I mentioned, the total operation quantity is 1,800,000 tons. And in China, it's 1,250,000. And overseas is 550,000 tons. Actually, nowadays, the low-loss connectors are very popular in the new transmission lines. Here, I share some principle of the low-loss connector and the types. And actually, the principle of low-loss connector is to increase the current capacity, increase the cross-section of the conductive part. And the basic methods are replace the steel core with aluminum alloy wires and also use shaped aluminum wires. And these are 3 typical designs. The ACAR connector adopts the aluminum alloy as a strengthened core. The AAAC connector adopts all aluminum alloy for both the strengthened core and the conductive area. And this ACSR AWTW connector adopts shaped aluminum wires as a connecting part, and the high-strength aluminum-clad steel wires as a strengthened core. By this design, we will reduce the core area and increase the conductive cross-section. Here is a case design of ACAR connector. It adopts 55.25% ICS aluminum alloy as the conducting part, and this 55.25% ICS aluminum alloy is used to replace the steel core as a strengthened core, but it has a function of conducting the transmission and the current. So from these parameters, we can see with the same diameter as SSR, the ACAR connector achieve the lower DC resistance and the lower unit weight. And the line loss will be reduced about 4% for the round wire. And for the shaped wire, it will be reduced about 50% of the line loss. This is a case design of 59% of the AAC connector, the 59% ICS aluminum alloy wire is adopted for both to complete the all connector. And from the parameter we can see same diameter, the DC resistance is reduced and the unit weight is also reduced. The overhead line loss will be reduced about 4%. So because of the lower weight, the tower for ACAR and AAC will be reduced with the smaller size and the smaller foundation. So the comprehensive construction of the transmission line will be reduced a lot. Here is another example design of ACSR AWTW. The shaped aluminum wire is adopted to replace the round wire. And the high strength aluminum-clad steel wire is used to replace the galvanized steel wire. The aluminum-clad steel wire also serves as a conducting part. From the parameters we can see, the DC resistance is reduced much, and still keeping the same unit weight and the same tensile strength as our SSR connector. This connector will reduce the overhead line loss by about 12%. This is a similar design as SSR LTW. The difference is the outer layer is a thermal-resistant aluminum alloy. And this thermal-resistant aluminum alloy can work at a higher temperature, 150 degrees. So it will increase the current capacity about 66%. And in the normal operation, the overhead line loss will also be reduced about 12%. For the new line, if we want to greatly increase the current capacity for the reconstruction line, we need to consider some more special solutions of operating conductors. And here, I will show some parameters of the thermal aluminum alloy and hydrogen aluminum. Actually, the principle, one principle of the operating conductor is to adopt the thermal resistant aluminum alloy, because it can work at a higher temperature than the hydrogen aluminum wire. The TAL, thermal resistant aluminum alloy, the maximum working temperature is 150 degrees. The operating ratio is 1.5. The STAL or ZTAL, it is a super thermal resistant aluminum alloy. The maximum working temperature is 210 degrees, and the operating ratio is 2.0. Besides that, ZTT also developed a high conductivity for the hydrogen aluminum wire and the thermal resistant aluminum alloy. Here we can see the IC standard hydrogen aluminum has conductivity 61% ICS. ZTT hydrogen aluminum can reach up to 62.5% ICS. And the IEC standard TAL conductivity is 60% ICS, and ZTT standard is 61% ICS. This will reduce the line loss more effectively. With above materials, thermal-resistant aluminum alloys, and the strengthened cores, we can make different designs of operating conductor. Here's the one design, TSSR AW. The core is aluminum-clad steel, and the outer layer is a TAL wire, maximum working temperature 150 degrees. This design will increase the current capacity by 50% to 80%. And the installation method, the same as the old SSR connector. This is another design of INVA connector. It's based on the unique material of INVA. The core to change the older connector, and which was a big cost for the reconstruction. And although the installation method is same as the old SLR connector, convenient for the installation. Here is another design of gap connector. It is based on the unique structure of gap. The core is extra high strength steel wire. It can support the complete tension of the tower, of the connector, of the complete connector. And the outer layer is STL. It will increase current capacity by 100%. And in between, there is a gap, and so that the steel core can freely slip for the sag adjusting during the installation. And the sag will not be increased at the maximum working temperature. And there is no need to change tower too. And the difference is that the connector low sag is achieved through a little different process in the installation. Here is a comparison of the case design of the SSR connector, TSSR connector, EVA connector, and the gap connector. So from the parameters, we can see these operating connectors can increase the current capacity by 50% to 100%, while they're still keeping the smaller diameter and less unit weight and similar tensile strength. So the sag will not be increased. Actually, for detailed technical issues, we can adjust the core and conductive cross-section according to the different sag requirement of the transmission line. Besides the low-loss connectors and the operating connectors, ZTT can also give solutions of functional connectors adapted to different environments. Here, I'd like to share some main types and features of some functional connectors due to some various applications. The first, the low wind pressure connector. It is a use big wind area, and it has some special shaped wire. The connector for big span and the icing area usually have the high tension weight ratio to ensure the safety. And the connector for renewable energy also the N-1 requirement. The corrosion area, it adopted the nano conversion coating with good resistance to the salt spray corrosion and the UV rays. Here comes to the thinking of the connectors for renewable energy. As we all know, the obvious feature of renewable energy is low utilization hours. So the question is, shall we adopt a large size conventional connector for the peak current value? I think the answer is no, and it's not necessary and not recommended. There are some reasons. Actually, the average output of the renewable energy is really 40% of the peak value. So if we adopt conventional connector, so it will be large size. This will increase the connect cost. This will further increase the comprehensive construction cost. And besides the renewable energy has to face some problem of the fluctuating output and also requires the N-1 capability. So due to the low utilization hours, the adoption of large size conventional connector will be quite a waste, not good economy. So instead, we recommend this TSSR-AW connector. We also call it the low-loss thermal connector. It adopts the high conductivity aluminum thermal-resistant aluminum alloy with 61% ICS conductivity. And the strengthened core is aluminum-clad steel wire, also serve as both connecting part and a strengthened material. So this will reduce the line loss at both the normal working temperature and the maximum working temperature. And furthermore, this high temperature aluminum alloy can work and meet the peak value of the renewable energy output. And this small size connector can reduce the connector cost by 30%. And similarly, it will reduce the tower cost. Here is a simulation of connector selection for a wind farm plant. And from the capacity, we can see the ACSR 630 connector and the TSSR 400 connector can both meet the peak value of the transmission capacity. But which one is having better economy? We will see from the annual cost comparison based on the whole life cycle. Let's say the transmission life cycles 40 years, 2 years construction period, and under the different energy recovery rate, the annual cost of TSR-AW 400 connector is the lowest. So it has a more economic solution. And last but not least, I will share the ZTD capability and one-stop solution. As a group company with 76 plants, ZTD offer one-stop solution of the transmission line products. We provide a wide range of transmission products like conductor, OPGW, OPPC, ADSS, and hardware fittings, insulators, and power switch gears. We can say for the transmission line, we can do all the products except the tower. And from the raw material to the finished product, ZTD meet the international standards like IEC, ASTM, and EN, AS Australian standard, and different countries' standards. And these products are type tested in the domestic and international labs, such as the Kinectrix in Canada, and the SAG in Germany, and the Wiki in Hungary, and TICW in China. We also have our own independent test center with the ELAC MRA and CNAS certificate. And we have a friendly cooperation with some reputed organizations like TUV, VDE, EMTC, and Securi. Our test center has some unique capability to conduct some special tests for analysis and research. And this is a simulated transmission line with 100 meters span. It is the only one in China manufacturers. It is used to analyze the real line operation and can monitor the temperature, current capacity, sag and tension at the same time. Here are some other key tester instruments for the breaking load and the stress strain test, the materials elemental analysis, the salt spray test chamber, and some vibration absorption test analysis for the fittings, as well as the shift test device for the installation analysis. So with these tests, we ensure the quality control from the raw material to the finished products, and also the installation operation. Here are some reference of our overseas end users. Okay, that's all for my presentation. Thank you for listening.